We're in the last session. And I'll first introduce the instructions, and then I'll introduce the panel chair, and then they can do some other introductions. So we're using a webpage called Pigeonhole. So if you go to www.pigeonhole.at, not com.at, and there's a passcode, SENSE.nano 2018. You can log in, and you'll see questions that have been asked. I will act as a moderator, so I will not let any inappropriate questions come through. So we've had some, yes. Won't let the inappropriate ones come through. But then you'll see the questions that are being asked. You can vote on questions if you really want that question to be asked. And our panel chair will also see those questions, and we'll use that to help facilitate Q&A for questions that are coming up during the discussion. But then also we can pull from as that turned over to the audience. So first, I will introduce Heather Goldstone. Heather is an MIT alum, a scientist and journalist. I won't say turned journalist as you have here. A scientist and journalist whose work introduces audiences to the excitement of discovery and the importance of science in our daily lives. She's science correspondent for WCAI and WGBH Radio and a host of Living Lab Radio, a weekly live interview show about science and culture. She holds a PhD in ocean science from MIT in Woods Hole. Her reporting on science and the environment has appeared on NPR, PBS NewsHour, The Takeaway, and PRI's The World. In 2014, she was recognized for the breadth of her reporting with WGBH's Margaret and Hans Ray Curious George Producer Award. So I'll turn it over and invite her to take charge of the panel, and please ask questions as we go. Thank you.
Thank you so much. And I'm honored to be here. I am definitely the non-expert in the room, but that's kind of my job. And so we are here to, I wouldn't say tie up loose ends, but maybe put a bow on things a bit. There are still a few more speakers after us, but to pull out some threads all the way from this morning's first keynote and all the presentations that we've heard today, and talk a little bit about how this all comes together in the context of food production and also broader societal implications. So as with previous speakers, you have the full bios in your books. We won't do extended introductions, but we do have two panelists whom you have not yet heard from today, and so I'd like to ask them actually to introduce themselves, and we're going to start right here next to me with Paul Sellew, who is the CEO of Little Leaf Farms. He is the producer of the lettuce that we ate today at lunch, and he is an actual farmer. And so we're going to hear from him as an end user potentially of a lot of the technologies and techniques that we've been hearing about today. And Paul, why don't you start by introducing us first of all to Little Leaf Farms, what it is currently, and then what you envision it could be if we put some more of these sensing technologies into play.
Great. Thanks, Heather, and thank you for inviting me to participate today. So I'm founder and CEO of Little Leaf Farms, which is a state-of-the-art, 5-acre, fully automated, high-technology grower of leafy greens. I'm a New England farm boy. My family runs the largest ag business in Connecticut. A couple hundred acres of greenhouse, what I would call lower tech greenhouses in Connecticut, mostly growing ornamental plants that my brother Mark runs. I pursued food, and I looked at Massachusetts and New England in general. We bring in about 90% of the food that we eat. And as far as food security and as far as just an economic opportunity, especially with produce, which is a value on freshness. So right now we're being served about 95 to 98% of all the leafy greens are grown in Arizona and California, and they ship throughout North America. So I felt there was an opportunity to basically compete against them and deliver a higher quality, fresher product, and that's what we've been able to do with Little Leaf right now. We, from a startup, typical startup, broke ground in 2015 and went through the craziness of shaking out the system, making sure all of our sensors all tied back to our PLCs and was all being done correctly. It's always a challenge, but we're working well now. We're selling millions of packages of lettuce to over 1,000 grocery stores and leading food service establishments, and I think we're basically showing that there can be a local sustainable food production model. And I'm a big proponent of using greenhouses because there's a lot of talk about vertical farming and growing inside warehouses and urban agriculture, and it's all technologically possible, but basically how much are people willing to pay for lettuce. So that's why I'm a big believer in greenhouses, because I'm a big believer in the sun. And we use supplemental grow lights as well, but we really rely on sun in our system. So that's why it was interesting listening to Gabriella talk about photosynthesis, something near and dear to my heart. So look forward to participating. That's a little bit about Little Leaf.
Give us a little bit more detail about how your greenhouse works, because this is probably not what most people think of when they think of a greenhouse. I mean, besides the fact that it's a 5-acre greenhouse.
Yeah, well, United States is a field agriculture country. We're the largest agricultural producer in the world, so we have a very sophisticated agricultural system, but we are not sophisticated in greenhouses. So I relied on European partners. My growing system, believe it or not, I brought over from Finland, which, a country of 5 million people, has 100 acres of lettuce greenhouses, which is about double what we have in North America. My greenhouse and my lighting and water technical systems are Dutch. So this is a second go-around in greenhouse. I also built a 42-acre tomato greenhouse up in Maine in Backyard Farms about 10 years ago. And that's when I first realized that the New England consumer in particular really put a value on locally grown, higher quality, fresher produce. So with Little Leaf, unlike Backyard Farms, which employs today about 300 people, I didn't feel I could get 300 farm workers here in Massachusetts with under 3% unemployment. So we built a highly automated system. No human hand touches the product from seeding to harvest, and we have a very specialized system where as the plants grow, they separate automatically as they travel through the greenhouse. So therefore, we maximize plant density per square meter, and obviously all the associated efficiencies by doing that. And I'm a believer in supplemental grow lights, and we measure that. We measure light, we measure humidity, we measure temperature, we measure everything. The one thing that we don't measure in real time is nutrients in our fertigation solution, which is one of the reasons why I was excited to participate today. So talking to the gentleman from Agilent, we now currently grab our fertigation water, send it to a lab once a week, and I'm waiting 48 to 72 hours for results back as compared to real-time sensing and then an automated pulsing system so I can keep it within the band for the macro and micronutrients for optimum plant growth. So I hope something comes out of that, out of my participation here. But ultimately, at the end of the day, we're trying to be a proponent of local, sustainably grown food. And with, as I mentioned, with over 90% brought in from outside the state, we think there's a lot of legs and a lot of room to grow.
Thank you so much. The other panelist that we've not yet heard from today is Professor Michael Strano, Carbon Dubs Professor of Chemical Engineering at MIT. And I was hoping you could introduce yourself and some of your work on maybe what the plant of the future might look like.
Sure, wonderful, great, good. Yeah, in fact, in this context, I'm also the lead PI on a Singapore MIT partnership called DSTAP, Disruptive and Sustainable Technology for Agricultural Precision, and it's a center funded at $40 million over the next 5 years to apply some of my group's technology to monitor the internal biochemical signaling of plants in real time. So my group at MIT, we have figured out how to put very small sensors, nanometer scale sensors, into very exotic places inside of a living plant, inside the chloroplast, inside the plant cell, into the vasculature, and we can monitor, we can turn them into chemical sensors that then beam that information out and can even send it to your cell phone. So if you look online, you'll see we've made an explosive sensing plant. It can detect explosives in soil and send that information to your cell phone. We've made plants that can, we can detect the stomata opening and closing on the surface of a plant and monitor in real time the plant's water usage. We've also made a light emitting plant. So this area where you can take very small sensors, control where they go inside the living plant, is giving us new information about how plant signaling works, and that's the effort of our center. We're focusing on problems particularly for urban farming. It's actually relevant to Paul's system as well. We're going to use these sensors to solve problems like shade avoidance. If you try to plant many plants, I'm not sure if it's true for lettuce, but if you try to plant many different types of crops at very tight pitch, which you would like to do for high yield, plants will, they have an evolutionarily conserved mechanism where they'll try to outcompete each other. It's called shade avoidance. They'll basically try to put all of their resources to growing taller than the next plant, and of course yield suffers. And so the shade avoidance is the shade avoidance syndrome that plants demonstrate is a chronic problem. It really reduces yields. I don't know if it's a problem for Paul, but it's something that we're going to address in our center. Also, pest and wound healing, damage, and disease. So these sensors can provide new and interesting information to engineer new plants. We're partnering with the Tomesic Life Science Laboratory in Singapore. They'll be using this information to further fundamental plant biology and also engineer new plants that can avoid these problems.
I have some follow-up questions for you, but I want to introduce our other two panelists. First, of course, just so everyone knows, we have John Fernández, who you heard from earlier, the director of MIT's Environmental Solutions Initiative, and of course, Craig Marvin of Agilent. Michael, I want to go back to these plants of the future that can detect everything and beam it out. I mean, a boost in photosynthesis, yes, one possible thing. As you said, detecting problems that might need to be addressed. Maybe getting over this shade avoidance syndrome, which I love calling evolution's result a syndrome, gets at exactly what we were hearing from Gabriella, right? That our end goal and evolution's end goal, not necessarily the same thing. But for me, raises a question of why address these specifically with nanotech, when we could go in and just knock out the genes that turn on shade avoidance. We could just go in and knock out the genes that turn on a sunscreen mechanism and do this perhaps genetically or through some other mechanism as opposed to nanotech.
So we don't. So the problem across the field generically is that we don't know those pathways yet. And so although we have genetic information, there are also phenotypes that are displayed in more complex settings. And also, so for example, the shade avoidance is a collective phenomena that plants demonstrate at maturity. It's hard to study. The biochemical signaling pathways still need to be elucidated. The advantage of our technology is that we can put sensors and probes in areas of the plant, tissues in the plant that are not accessible by any other type of probe. So in plant biology, normally you're growing a population of plants, you're grinding up materials and feeding it to a mass spec. Our paradigm is completely different with respect to sensing. We can probe a plant in real time. We can monitor it throughout its growth on the time scale of plants, weeks and months. And so the type of information we can find is very different. It's really a paradigm shift in plant biology. They're fundamentally not used to monitoring plants as an organism in real time at their own time scale. So our technologies are enabling that. I'll also say that part of the center is my colleague who's not here today. He's in Singapore, Rajiv Ram, who's an absolute, who's brilliant at shrinking Raman spectrometers. He can make Raman spectrometers the size of your watch. And he's part of the center focusing the Raman spectroscopy that can also probe, again, biochemical signaling inside the plant, reporting it in real time, and to address these problems. So hopefully I answered your question.
Yeah. Yep. So I would love to hear from all of you on this next point, which is that while I understand the need to boost our agricultural production, I'll be quite honest, I'm not sure I feel comfortable eating a Raman spectrometer for dinner with my salad. Maybe Paul, I'll start with you. Is that something that you feel comfortable growing as a product?
With greenhouses, you do have limitations. So as far as growing grains or other things like that, I don't think greenhouses are the solution. But for growing produce, we're about 25 times the yield over field. So it would take our 5 acres multiplied by 25, and that's how many acres would be required to duplicate our yield. So that's where I think controlled environment, where you're managing it in real time, and you're optimizing and taking away stress from the plants, it's amazing, the level of productivity that you can get.
But do you want your plants to be the sensors?
In a way, if you talk to my grower, you would say, not in the way I think you're thinking, but you would say that yes, the plants are the sensors, because the only people in our greenhouse are growers. And so they aren't in tune with those plants. So we have a human sensor that's looking at those plants in real time, you could say. And I'd love to learn more about your technology, but we're turning a crop over in 25 days. So whether it could make sense or not, I'm open to it.
Let me defend myself here. No, so there are a couple of different ways that we're deploying this technology. What I described was really a research tool that's providing the output. These are model plants we're studying in the lab, but we're getting information we've never been able to get before, and we're feeding that back into life science researchers, plant biologists who are going to use that understanding to make changes in practice and in agriculture and plant biology. But another technological implication product that we're working on is the idea of a sentinel plant. So this is not a plant that you would eat, or it would be isolated, very well contained, but otherwise placed in the condition with the agricultural crop. And there's a long tradition of this, having a sentinel plant. If you go to a vineyard, there's a tradition of having a very fragile rose or something at the head of the vineyard row, and it's supposed to be a sensitive indicator of damage to the plant. It turns out even in Paul's operation, he may have a pest control strategy that actually involves a sentinel plant, and there's a human that goes over and counts pests on a piece of glue paper and so forth. So we can wire up things like that. We can make a plant that we actually have a product. We actually have a system now that basically, if a single aphid bites a plant, it actually sends it sends a chemical signaling wave all throughout the plant. I can send every bite to your cell phone, actually. So you can actually make a sentinel plant that can detect the first bite of the first predator of a plant it's attractive to. And again, we're not proposing that you eat any spectrometers or strange things.
Although, Craig, you did in your presentation already allude to some of the potential environmental costs of this technology, while we've been mostly focusing today on the ways that this technology could create environmental benefits. There are some potential costs here. How much do we actually know about some of the risks, whether it's environmental or human health?
Well, yeah, it's actually interesting because the regulators, the environmental regulators, really don't have legislation, at least in this country, that governs nanomaterials. So there are countries around the globe. China, for example, doesn't allow biomass to be used to provide nutrients to agricultural fields because of concerns about nanomaterials that end up in that biomass. I think we're looking at something that it's a little bit of a two-sided coin, because if you look at the spray and pray opportunity to blanket fields with fertilizer, herbicides, and pesticides, that most of that runs off and goes into the water systems, watersheds, et cetera. That has a lot of waste to it. I think if you look at these focused applications of nanomaterials, that engineered nanoparticles that are filled with these type of things that are deposited at the root structure, I think you have a more localized distribution, a lower localized administration, and the demand or the potential impact on the environment is much less. So there's a cost-benefit analysis. The risk is that these nanomaterials are taken up into the plant, and they do respond, like my co-panelist said, in response to this. They will, the root exits change, there are changes to, amino acid composition, to fatty acids and things as they try to expel these products. It's yet to be known. What you'll see sometimes, there was work that was done at UCSB looking at cucumbers. And with a nanomaterial challenge, the plant actually puts all its energy into the fruit. So you get these hyper-sized fruits, which may have a lower quality than what would be done through natural purposes, but it's a preservation mechanism. Let me produce a big fruit so the seeds will go out and I potentially can continue. So it's not an easy question, and I think it remains to be seen what the economic impact or value would be to the industry.
John, I wonder if you could perhaps go another step with that. And are there efforts at MIT as the research on nanotech is expanding to also look at this in a full life cycle way in terms of the potential environmental impacts, recapture of nanotech, recycling of any of that sort of thing?
Right. Well, so let me back up here for a second because I wanted to address the need for increasing the production of food. We've heard that a couple of times this afternoon. I'd like to sort of put a little bit more of some detail on that. It's not just the increase in the production, but it's also the improvement in the distribution of food, because we're producing plenty of food. It's just that the distribution is not particularly efficient, and it's not spread evenly so that the need is being covered. So in terms of nanotechnologies, but other technologies that would service the highest efficiency in different modes of food production, whether it be urban agriculture or just improved land-based agriculture, I think there's a lot of work to be done. Sensor technologies are obviously part of this, and especially when you're really parsing very carefully the resources that are inputs into a food system that is located in a city, for example, where land rents are much, much higher than outside of a city. So much of the work that I do is the nexus between urbanization and economics, and urban agriculture is nowhere near being economical in pretty much every city in the world. And in most places, it's also more material and energy intensive. So there's a lot of work to get beyond that and to provide the value that's really appropriate in that particular location. And I think some of the technologies that we've been talking about today, some of the approaches that we've been seeing are interesting prospects, but there's a great deal more work to do.
At one point today, I went into daydream mode and I took the tractor that feels more like the Starship Enterprise that we heard about very first thing this morning, and your description of these 5, 10, 40-acre greenhouses and automation and sensors, and had this vision of the future of America that was a bunch of huge cities around the edges, and just the middle of the country is uninhabited, automated farmland. Like, is that where we're headed in terms of urbanization and still having food production, or are we going to need to marry the two spaces better than that?
Well, where we are today is we're kind of there in some parts of the country, along with oil production and fracking, let's not forget, has also populate has also come into the middle of the country. But no, I mean, I think the two principles by which we have found there's a lot of prospect for technology and policy and design development is in decentralizing the production and acquisition and distribution of resources, so food, water, energy, and then the localization, again, of the production and distribution of those resources. And so part of what we see now is that cities are looking at higher resolutions at how neighborhoods themselves can become semi-autonomous or semi-sustainable within their bounds, or at least more resilient than they have been in the past. And I think food has a huge part in that. So I'm hoping that the future is not what you describe, that there is more of a infusion into cities of urban agriculture that is appropriately designed and engineered for the right value, for the right purpose.
So what does that, is there any way to know in advance what that looks like, or is that a building by building, city by city determination?
I'll add a little here to what Paul was saying before. I do think that so what we found in our research, and we did a full survey of urban agriculture technologies and found that one of the pieces that is really lacking is that there's very little tracking of the inputs, the actual, what you were describing before, what are the nutrient inputs and other inputs necessary to run a farm on the roof of a building. And I think that kind of resolution is necessary because that impacts the economics of the operation. It impacts the sustainability, the life cycle sustainability of that operation. And at the end of the day, we really want to scale up systems that are going to be more sustainable, less energy and less material intensive than land-based agriculture. Yeah.
Yeah, please jump in, Paul.
One thing to add on that is that I'm a big believer in what I refer to as peri-urban. So the perimeter of urban, the suburbs. So, I mean, I live in Carlisle, and, you know, Lincoln, Carlisle, Concord, I mean, traditionally these were farming communities that fed Boston. So clearly now they're sort of nice suburbs that feed Boston, sort of people to go work in Boston. But I went out a little bit farther to Devon, so I'm 35 miles from downtown Boston, but you don't have to deal with what you have to deal with to develop anything in an urban environment. So, you know, there's plenty of land in the United States. And so I'm a big believer in peri-urban, and you're close enough so that you're local, but then you don't have to deal with sort of the issues, high energy costs, high labor costs, complicated development in urban areas, high, you know, very expensive real estate. But then you get the benefits of being close to the urban market. So that's kind of how we're thinking about the opportunity.
Well, while you're on that note, we've got a couple of questions actually from the audience, kind of on the economics end of things, asking what is, and I think you've already touched on this a bit, but what is the business case for greenhouse automation systems in the US, and what do you think is the size of the current market?
It's very new. When I did backyard farms about 10 years ago, we built a 25-acre greenhouse, which we felt was the smallest to basically economically supply the grocery trade for tomatoes in New England. Now it's 42 acres, and believe it or not, that's not considered large. That's about mid-scale for tomatoes. And the tomatoes and cucumbers and peppers and eggplants, those are sort of well-established greenhouse crops right now. Lettuce is an emerging crop. Right now, it's still dominated by California field production, but you might have been tracking the romaine E. coli 0157 scare. It was identified in Yuma, Arizona, and they have not identified the individual farm. So you have serious food safety issues in dealing with this, and this is still with a lot of regulation. Now, the FDA is involved with FSMA overseeing produce. So I think from a food safety standpoint and with automation and using natural sunlight, I'm a big believer that I think crops like leafy greens have a lot of room to grow, and we're making money. So, I mean, you know, from that standpoint, I'm competing against California, and we're making money as a company.
And in terms of the cost, as our farming becomes more and more technical, and Paul also, if you'd like to jump in on this, I guess I'll highlight here this particular question, but how high does the cost get? And how do we balance the cost of the technology and the cost of our food against the fact that, I mean, you've already noted that geographically there's a disconnect in terms of where food is produced and where it's needed, but in terms of the cost and the economic resources, the technology needed to grow the food and the funds available to deploy that technology. It seems like there's a mismatch. Go ahead.
Me?
Yes.
On the cost. Not a question for me, I think.
No?
No. So what I can say is, you know, I think one thing to highlight here is on the life cycle costs, we should take into consideration the co-benefits of growing locally and growing in a more regional way, valuing the peri-urban zone and localizing production, because the co-benefits of reduced air pollution from transportation, reduced carbon emissions from transportation is something that's just not valued, not priced right now. And I think those sorts of co-benefits, aside from many other co-benefits, like knowing where your food comes from, having fresher produce, maybe even if it's very local, having some connection to the production of food, those co-benefits are difficult to price, but are certainly valuable. I think that's all I can say on that question.
Michael, working internationally with the Singapore project, do you have any insight into
how different the economics and the market demand for these kinds of agricultural technologies are in other parts of the world?
I think I can say I'm from what I see in Singapore. They're taking an empirical approach. So you're seeing there are firms that are trying to adapt the Amazon warehouse model of indoor farming, urban farming, going the way of almost complete automation, maybe similar to Paul's setup, although not on the acre scale. Think of a warehouse, and then you have anything from low tech addressing really trying to keep the water and energy use down. And so Singapore is experimenting with different things. I think there's fierce competition. The economics, I think, and also the intellectual property are pretty tightly held. So it would be hard to extract that information. Paul's pretty upfront that he's making a profit, and but maybe you would be hard pressed to really get that information from my perspective.
Go ahead.
And one thing I want to add, and sometimes, especially with more technical crowds, there's a lack of appreciation for the market. And the market right now for produce is called grocery stores. And yes, Amazon, and yes, online, but if you look at the data, the overwhelming amount of produce is still bought at grocery stores. And it's about 55–60% grocery and the balance food service, which is institution and restaurants. So you have to fight your way into the grocery store. No buyer for produce in any grocery in the United States right now wakes up and wonders, am I going to be able to get whatever they're buying? The market in some respects is even overserved. So this notion of what we had to do is we had to put up all the capital. We had to take the risk of getting into the market and finding customers who are going to buy our product. And that is why I think this is going to go a little bit slower from an adoption standpoint, because that's a huge amount of capital risk that you put up front without really having anything sold. And I had a background and track record with backyard farms and tomatoes, which helped, but still there's no such thing as a contract. You have to fight your way in the market, and it's tough.
While we're on the topic of our current grocery and food distribution system, we've been talking mostly about the ways that technology could actually improve food production and yields, but food wastage. I think the statistic is half of all the food produced in the United States gets thrown away. Is nano sensors or better sensors along the shipping route maybe something for a Sentinel plant? Is that something for embedding sensors in packaging? How could we get better at knowing when something maybe is about to go off and try to prevent food waste and throw some technology at that?
Yeah, that's a good question, right? And so we could look into. So one of the things that one of the sensors we've developed actually can monitor the chemical signaling wave that's induced inside the plant when you damage it. And actually, one of the things we're finding. So when a plant is damaged, when a pest bites it, there's a redox signaling wave that moves all throughout the plant. One of the things we're finding is that the amplitude of that wave correlates with antioxidant, the antioxidant production in the plant itself. So it gives us a real-time monitor of the productions of antioxidants inside the plant, and this is broadly applicable to almost any crop. And so one application is that you could use this to study what happens to antioxidants and vitamins and molecules and things that we're interested in, things that preserve the plant, prevent early degradation, keep food riper, keep it preserved during shipping. So that's one way that technology can address that problem. Long term, I have my colleague Tim Swagger in the audience is making sensors that can monitor fruit ripening. So that's another area where nano sensors are playing a role in helping along the supply chain and keeping preventing waste production.
And then we have another question on the other end of perhaps the consumption spectrum, which is, and
Craig, you mentioned all of these different areas that Agilent is involved in, environment kind of being one of them. So I wonder if you could kind of blur the lines between some of those. Could we embed medical sensors into our food and consume them that way? Or are there other ways that we might blur the lines between agriculture and environment and health and medicine?
That's an interesting question. You didn't want to eat, some, small device to look at, the nutrient content of food. So trying to put a medical sensor in something I think would be a discussion that the consumer would really try to understand. I think rather than putting, a sensor in the food itself, I think that would give some indication of the health within the person who consumes it. I think being able to understand the composition of that foodstuff to try to identify if things do go off or there is some accumulation of detrimental product that maybe would take that out of the food chain and use it for some other purpose. The other thing that I think would be interesting in that regard might be the ability to use some of these plants to help remove dangerous chemicals from contaminated soils. If you could look at perhaps cabbages or thing in China, they're trying to look at cabbages to remove heavy metals from fields, et cetera. So if there was an opportunity to develop something in that regard from a sort of a remediation perspective as opposed to watching, if I eat this cabbage, what will happen to me as a human? But what can the plant tell us about its efficiency in extracting these dangerous chemicals from its environment? Could be of interest.
And then what? What happens to those plants after they've extracted everything
Well,
from
then
the soil that we
they
don't
would
want?
have to just be destroyed. So they would be, probably I know in certain areas of China, they'll just burn those and then, dispose of the ash. So
I want to emphasize how it's important also to think about, and I think we've seen some examples today, of applications of advanced technologies, nanoscale sensors in the global south. So if we're talking about agriculture, food production, an increase, doubling of the urban population in the next 30 years, and that's happening, 90% of that happening in the global south. Climate change affecting the global south disproportionately to us. The sorts of very inexpensive sensors that would improve the efficiencies because of the fact there's resource scarcity. Water is scarce, or fertilizers are scarce, energy is scarce, or unreliable. I think that kind of whole spectrum of development in sensors is extraordinarily important and just sometimes maybe more challenging because you have to do it super inexpensively. I think we saw the sensing heavy metals using cellulose, and the performance functions of that sensor were very stringent. Had to be flat. You had to be able to nail it. I mean, that's a kind of like extreme challenge for developing sensors that, and in very particular ways in food and resources in the global south, I think that should be on the table. We should be talking about this. It shouldn't just be about producing, food for, the global north. So I just want to put it out there. Not that I have any solutions, but just thought we'd talk about that.
So one thing to eliminate food waste, my last company was North America's largest food waste recycler. So I'm now on the other end of the spectrum, generating food. And so the number I've quoted, or I've seen quoted the most, is about 40% of our food is wasted. And that's harvest, post-harvest, processing, transportation, retail, and post-consumer. It's not one location. So what we have found is that our food waste at Little Leaf Farms, because we're so close to the market, is like under 1%. So the ability to, when you have a perishable product that we put 15 days, when we pack today, we put 15 days. And so, the retailers have 15 days as compared to 5, 6, 7 days oftentimes they have with West Coast product. So I think building and transforming our food system and making it more local, I think will really reduce food waste.
I don't know if we have an answer for this next question, but it seems to be a burning question from our audience. How does the decreasing biodiversity we're experiencing figure into this discussion?
So I could say a little bit about that. It just so happens that we have a project that we are developing now with the Ministry of the Environment in Colombia Colombia being a post-conflict country, and they are looking to stem what's a rising tide of land conversion in eastern Colombia, southeastern Colombia, in the Amazon. A direct consequence of that land conversion and conversion from dense Amazonian forest to grazed land for cows is the loss of habitat and impact on biodiversity. So being able to, so there's a direct connection here between being able to provide, for example, in that context, how do people in southeastern Colombia, of which there are a couple of cities of 30,000 people, how do they develop a sustainable food cycle, food system that doesn't require land conversion? Or how can they have alternatives to the kind of income that they can produce by converting land and raising cows and producing meat with more sustainable food alternatives? I mean, there's one connection there that we're very much involved in.
On a similar note, another one that's gotten a lot of votes here is, for the panelists, what are your thoughts on, quote, impossible meat, plant-based food injected with proteins and nutrients? Is it safe and scalable, and are we shifting away from using livestock for meat?
God, I'm incredibly bullish on that. So Impossible Meats is one. The other is Beyond Meat, which is run by a friend of mine, Ethan Brown. I know enough a little bit to be dangerous, but I've eaten that. It's plant-based and it tastes good. They even now have, I don't know whether it's beet juice, so you put it on the grill and beet juice, you know what that's supposed to represent. And bottom line, it tastes good. And I think it's fantastic.
Anyone else want to jump in there?
Can't comment on that.
I will say I just interviewed someone this past week about not plant-based meat substitutes, but actually cellular agriculture. So a whole other technology from what we're talking about today, but actually growing animal muscle tissue in a lab or lab-based setting. So it seems like we've got all sorts of things on the horizon for trying to create protein without the methane and land use and other issues that our current meat production system has. I love this one, and we were just talking about this actually before the panel, which is, would it be possible for MIT to grow the food that MIT consumes? Either of you go ahead and jump in. You can both take a turn at it.
What do you think, John?
So I'm going to answer that in a sort of an indirect way. So again, part of the work that I do as a researcher, not at the ESI, is in this field called urban metabolism. And so we account for the resources required of cities. And so part of the reason I started this work about 10 years ago was because there was a lot of rhetoric about sustainable cities or net zero energy cities, and there's never been in the history of mankind any human settlement that's been sustainable within its boundaries. Not a Neolithic village 6,000 years, 8,000 years ago, or today's highest tech Northern European cities. They still need external inputs, and they produce outputs. So it's not viable, it's not smart, it would be super expensive to try to grow food for the MIT campus within the boundaries of the campus. And there's a really very bright silver lining to that thought, and that is that we need to cooperate and we need to associate with the city of Cambridge, state of Massachusetts, the region, and so we can be the consumers of sustainable food and renewable energy, but we need to associate with the providers of that. We're not going to be able to produce that on campus. So the answer is no. I wouldn't really even want to try it, and I can provide some hard numbers on that. There's actually, I want to just give some note to a class that was run this past semester Amanda, help me here. So Timothy Gutowski and Julie Newman ran a class on what would be a carbon neutral campus. What would it take to do that? And it's a good analogy to what would be a food sustainable or autonomous campus. And it's not really possible. It's not even something you'd want to try. It simply belies the numbers aren't there, the technology isn't there, it's super expensive, and it's probably not a smart thing to do.
Michael, go ahead.
So I'm going to take the opposite view of John. I completely disagree. I actually think that we should, I think that the numbers that he would present actually are based on technology today. It's really in the spirit of MIT. If you're an MIT student, maybe you could email your nearest administrator and support putting a greenhouse on top of every rooftop of the buildings that we have at MIT, and let's treat it more of a target for innovation. It's true the numbers don't come out now, but when has that ever stopped us? If you look several decades ago, conventional agricultural productivity per hectare and it went up almost many times. I mean, we experienced almost a dramatic agricultural revolution over the past few decades. I view Paul's work and the work of people like him, we're just at the start. And think about from everything from agricultural practice to plants that are better like bred and engineered for that environment, overcoming shade avoidance. Can we increase productivity? And the MIT campus should view it more as a research objective, right? And if we build the infrastructure, we can get faculty involved and interested in solving that challenge. So sorry, John, I have to.
Can I?
That's okay, but I'm actually
until those greenhouses on MIT are up and running. There's one about 35 miles away that might be able to help. So.
And I'm going to reciprocate and disagree again. And so my point is not that we shouldn't have the research challenge. The research challenge should absolutely be there for breakthroughs in food production technologies and the full spectrum of whatever that means. My real interest is that MIT has a role in moving the market. And in moving the market, we should be interacting with all of our vendors. We just went through a whole process of hiring or deciding on the contract for on-campus dining. This is a big issue, sustainability, and we really push them very, very hard. And so my answer was that we need to push the market, the renewable energy market. We need to push the food market. We need to push the procurement generally, and be part of a larger civic voice in moving MIT towards sustainability. That would not, so now I'm kind of agreeing with you, that would not compromise at all the blue sky, future is to be made kind of notion that MIT's always been a part of and we should do. And just so you know, I think Michael and I have traded emails on, there is the prospect of a plant research facility here on campus. We're looking for a site, and we're looking to link that to a community garden and maybe other parts. So there's a future there.
I want to shift gears a little bit. There are a number of questions from the audience that along the lines of, could we use nanotechnology to better monitor roots and mycorrhizae and symbiosis? Could we use nanotechnology to monitor soil chemistry? Could we use nanotechnology to monitor responses to climate change? A whole bunch of could we use nanotechnology too? And I'm guessing the answers in most of those cases is, if we wanted to, yes, we could. And I want to kind of go a step beyond that, which is what at the moment is the legal framework for thinking about doing those kinds of things? Is there a legal framework? I mean, we've had genetically modified organisms in our food system for years and are just maybe getting to the point of having labels and more consumer information about that. Is there a legal framework, and also what should the framework be for informed consumers when it comes to nanotechnology?
So before we get to the legal framework, I do want to make a pitch on the value of an effort to get in front of the environmental consequences of nanomaterials and nanotechnologies in the environment. My analogy now with what the ESI is funding is a project on seabed mining. So we've funded Tom Peacock, professor of mechanical engineering, to look at what are the projected environmental consequences of scaling up seabed, the seafloor mining in the Pacific Ocean, and huge tracts of the seabed. What happens when you scrape that seabed? What happens to the local ecology? What happens to the dispersion of those tailings? And it's one of the, as Tom points out, it's one of the only, and maybe the first, large-scale extraction activity that our species has launched into, preceded by a really intensive environmental study. And I think this is something that we should, at the same time, we should be looking into, and we are, and there are some projects that are looking into the environmental consequences of the dispersion of nanoscale materials, sensors, material systems. So, yeah.
Can I comment? So there's something that I'm missing here in the discussion, and that's I mean, as a practitioner, as an inventor and a practitioner of the technology, I guess I'm not seeing the leap from so the questions that you listed were can we use nanotechnology to monitor this or probe that, but then somehow there's a missing leap that I'm not getting to where but we're going to eat it and we're going to release it into the environment. I don't fully understand. There's a step missing there, and I'm someone who invents and uses and thinks of, and so maybe there's something that I'm missing. You know, I guess my point is that you know, we can use these systems as research tools. I guess you're envisioning wiring up or sensing every single plant in your field, and maybe doing that even on the product itself. And I think we don't have to do that at all. It's not a we wouldn't like a mass spectrometer is used in plant biology research all the time. We never ask about like what happens if parts of the mass spectrometer we eat it. There's something that I'm missing there. So maybe is there? Yeah. Do you want to clarify?
Could I try to? Because one thing that you spoke about, Michael, was this idea of a sentinel plant. Yeah. Now that where you could do what you do from the standpoint of putting whatever nano devices in that, and then it's not going to end up in one of my containers that I'm going to be feeding people with. But then I can use it as what you call it, as a sentinel plant. That's where I think makes sense. But as a marketer of food, the idea of like trying to explain to consumers that you have nanoparticles of food in here in any kind of a coherent way just doesn't, you don't want to get into that kind of discussion.
Yeah, I'm not trying to pour cold water on anything. I think, I guess the step in between for me is we can envision many different ways of using nanotech. Is there a legal framework? Is there any regulation or permit that you have to get in order to go out and monitor that tree or monitor that field using this technology? And because whether or not the fears and concerns are founded, just as there are widespread concerns among the American public about genetically modified organisms, there's a lot of fear about nanotech. And so, you know, what are the ways in which, as an inventor and a practitioner, you can envision kind of, as you said, this is another potential obstacle to get in front of. How do we communicate to the public what this technology is, how it's being used, and how it's being used responsibly, and what the benefits are?
Well, I think I can specify. Yeah, it's an interesting question to ask. Why there was a GMO backlash, and there hasn't really been one in nanotech. And actually, so I have a thought on that, and that's because nanotechnology is one of the first scientific disciplines to rise up with in parallel a scientific field devoted to studying its toxicology and safety. So there's a whole field, it's actually pretty large, actually, called nanotoxicology, and all it does is actually study each nanomaterial. It studies mechanisms, why, what is safe, what's not. So we have things like gross nanoparticles, right? We have we actually don't have gross GMO, or there wasn't, in a way, maybe we can learn a lesson from that. There was, in the GMO space, there was kind of an automatic, maybe like a self-congratulatory, this works fine. And maybe in going forward, because I mean, now we're seeing the advent of CRISPR, and so the question is that safe? I'm going to make a recommendation here. We should have a field of CRISPR toxicology. We should start it right now. And just like as the technology develops, people should be looking at like off-target binding and what are some of the problems. I think when the public turns its attention to this technology, they want to know that it's safe. They want to see that people are studying it, and they want to know what is safe. When we say nanotech, I got to stress how broad you're saying. You're actually saying like molecules. That's what you're saying. Like, are these molecules safe? You're breathing in 5,000 nanoparticles per cc right now. If I light a candle, it would be 1 million. And you're like, what are those particles? In sea spray, there's tens of thousands. Like, what are those particles? You've eaten and smeared on your skin and breathed in pounds of nanoparticles per year. All of you have. And so the question is, which ones are they? And are they safe? And have we engineered them? And they're already in the environment. And I guess the question, I'm not being flippant about the question, is if we engineer a particle that we don't want to release, can we track it? And is there regulation? Or anyways, it's something to think more about.
I mean, that was, just sorry to cut you off, but that essentially you said in a much more coherent and eloquent way what I was trying to say before, which is getting ahead of or alongside the research and environmental awareness, attention, study in a rigorous scientific way and getting ahead of any kind of backlash, which is because of misunderstanding, or that's basically what I was.
Craig, you've been nodding along down there.
Yeah, so no, what I was going to say, because when you say nanotechnology, there are two components to that. We had questions about could we monitor or sense something using these little nanosensors. That's completely different than trying to use nanomaterials, engineered nanoparticles for agricultural benefit. When you look at the food production, the ultimate measure of what the success is going to be is is the consumer willing to pay for the food that you're going to produce. So from a production standpoint, it's much like what you see in the laboratory industry or the instrument industry. There's a certain market value that the consumer will bear for that technology. And that's sort of the ceiling of where the producer can go. And ultimately what that producer then tries to do, how can I work to reduce my cost of operation? And that's where I think the nanotechnology offers an advantage. You can potentially get these materials that allow you to reduce these chemical costs to, improve yields or just to maintain yields, I guess, not necessarily producing more food, but reducing the cost to produce the same amount of food. And understanding the ramifications of utilization of those nanomaterials, where do they end up in the plant, where do they end up in the environment, I think we have a responsibility to investigate that so we can articulate it to the regulatory community, so we can articulate it to the consumer community, and everyone feels comfortable that we're actually doing something that benefits society and isn't really a rush to, okay, now we're going to make more money, but in the long run, guess what? We found out that we put more people at risk. And I think that is, I agree with John and Michael, that we need to be responsible in how we approach this.
I want to shift gears a little bit here. I have a question that's also been on my mind today, which is as we put a growing number of sensors into a growing number of sectors, we're creating a lot of data. What needs to be happening in the data analysis, AI, machine learning space to effectively utilize all of this data?
Well, right. So actually, you're seeing, So I'll answer as a practitioner. You're seeing really a revolution in what we define as a sensor. This is something that's not universally agreed upon, but you're seeing a new definition of a sensor emerge as not an actual physical object. Like there's a part of the community that wouldn't say a small nanoparticle is a sensor. They think of it more of as an algorithm. A set of a mathematical way of treating a diverse set of data inputs to measure something. And that's going to have profound changes in how we handle these large data streams. So you don't have to actually recreate laboratory precision in the field. You can use proxy metrics. I think anyway, it partly answers your question. One way to deal with the problem of drowning in data is just not to generate it. We can use smarter ways to get at the answer that we want. There are other ways, like sensor compression is a way of making sensors themselves that take the huge amounts of data and already compress it or synthesize it into the knowledge that we want and just beam that. But otherwise, it is an important problem.
I mean, we're doing a lot of that right now. So, and a lot of things that we measure in real time, right? And so, you know, we know what we're trying to meet. The classic one is light, right? We have light sensors in the greenhouse. We measure light in the par light spectrum in micromoles per meter squared per second, and then we roll that up. We count those photons. We roll it up into what we call a daily light integral. And then we know what daily light integral, which is moles per meter squared per day of par light for that plant, right? So, and then we have basically an algorithm that manages the shade curtains, the grow lights to make sure that we hit our DLI. That's just one example. A lot of that is happening right now.
If I could, what I think you see also is from an environmental standpoint, you know, the sensor itself is part of, you know, perhaps an array of devices that will measure various chemicals that could be in the air or in the water. And from an environmental standpoint, these are sort of like early warning systems. You know, one of the things that, you know, people that are concerned about hydrocarbon processing or chemical industries in China, USA, Europe, et cetera, are very concerned about what happens if we have a leak. How are we going to be able to identify the leak very quickly, and how are we going to be able to send a warning out to the population, depending upon which way the wind's blowing, so that we could move get people to vacate the area. So as you look at that, I think, you know, the sensors have a functionality. The data that's there are mapping systems, but, you know, I can freely admit that some of the companies that are making these types of devices, you ask them, what do you do with the sensor? And, you know, well, it'll tell if you want to go to the west side or the east side of the city to take your kids out to the park on Sunday afternoon. And so I think that's where the EPA and MEP and the CEN are trying to understand how could they leverage this big data to get something that's tangible and of value to the population.
John, we've just talked about how diverse, if you're going to try to use this term nanotech and all of the different manifestations. I mean, the fact that there are nanoparticles in your sunscreen, and that's very different than having a carbon nanotube inside of a plant's leaf, or having some sort of living ink tattoo that we heard about earlier today that's monitoring health systems, right? There's a huge range of these, but it's all part of a broader societal trend of just more and more sensors, more and more information and more data, which can be overwhelming, but also can be really key to sustainability issues. So how do you see our cities of the future, whether it's truly nano sensors or just more embedded sensors, how are we going to use this information to both understand the impacts of climate change and also start addressing climate change?
Yeah, I think the parallel story with the increase in the amount of data is also the better articulation of what our goals are. I do think that there is a better understanding of the direction that not just cities, but all sorts of human parts of the economy need to transform into low carbon future, into more sustainable forms. And I think the goals are becoming clearer and clearer. Earlier today, we heard about the Sustainable Development Goals. Those are very particular to priorities that are global, but you could also conceive of them locally. So you just mentioned the acquisition of data on, say, air quality in a very localized way, let's say along a road, and you might want to know that in case you want to take your kids to one side of the park or the other side of the park. There's a company in Southern California, Northern California called Aclima, which does, so you know this company, so you're thinking about this. So, you know, the idea that people are better aware that, that particulate matter is really unhealthy. That's, you know, better known than it used to be. I think better information about what the link is between the climate, the other environmental challenges linked to climate change, like air pollution from coal-fired power plants, and how that affects you personally, locally, and then what do you do about it? You need to have better data, you need to have a better sense of what's actually going on, sometimes in a very tight temporal resolution, you know, on a diurnal basis or even subdiurnal basis. So I think the answer to your question is that you know, there's an enormous mountain of data that's accumulating. There's a lot of big data. There's a lot of really messy, low-quality data. I think alongside that, the better we are able to prioritize our goals and articulate our goals, which I think we are doing. The National Climate Assessment Report, the next one, which will have a regional set of recommendations coming out in the fall, is an example of that for our country. So I think that's the positive side of the data story that I see.
Absolutely. Yes, absolutely.
Yeah, I think plants can actually play a significant role in trying to transform our economy to one that's sustainable and mitigates climate change. And this is an idea that maybe a good portion of you are not ready for, actually, but you can. I started this new field I called plant nanobionics. So if we shift our attention away from eating plants, so don't think about eating plants anymore. But we started in my lab at MIT asking the question: Can we engineer plants to perform the functions that we currently make things? We stamp out of plastic, we put circuit boards on. You know, can we give non-native functions to a living plant? Can we make a plant that is an autonomous light source or a Wi-Fi repeater or things that, you know, can we put them in our environment? And it's an interesting question to ask. There are several reasons for doing so. Plants are they have their own power source from photosynthesis. They store their own energy as saccharides. So they're somewhat of a combination of a solar cell and a battery. But they also can do other things. They can access water with seemingly very little input energy. I like to say they're doubly carbon negative because they store their energy as what was CO2, but they're also built from what was CO2. So they have a double negative carbon footprint. And they're many times they're a waste product. We pay to get rid of them, but they also self-repair. And so if we maybe it's the longer term vision. Can we think about instead of the objects that we throw into landfill, we stamp them out of plastic, we put circuit boards in them? Can we start to think about a living plant replacing those things in our environment? So we've started doing that, and you're not ready for it, but maybe one day you'll come around to thinking that that's a viable solution.
I don't know if I want to talk to my family through my plant, but I love the idea of, like, when you say nanobionics, I think plant superheroes, that they're going to be our plant superheroes as we face sustainability issues. Since we are sitting here in the Broad Institute and have been talking about food production, question here, although it's not actually an either or, which is likely to be more important, perhaps, in achieving better agricultural yields? Sensor technologies or gene editing technologies and modification of the plants? Any takers?
That's a tough question. Yeah, it's a broad question.
And given that it's prefaced with this is not an either or, we're not going to do just one or the other. Maybe it's where do we need to be focusing our more immediate attention?
I'll say it's a question for you, Paul. I'm going to put you on the spot.
Well, I mean, there is a negative consumer feeling about GMO food. I mean, that's just the reality. So personally, as an agricultural professional, I think there's a role for GMO. And if you look at sort of the human health safety aspects of it, to me, it's a non-issue. It works. But it's so much about, it's not just a technical argument, it's an emotional argument. And if you're going to be going to the consumers like we are with our own branded product, we put non-GMO on our label. So, you know, because we poll the customers, and it's just not a well-understood issue, but a lot of people won't buy the product without that non-GMO. And I'm not saying that, you know, that's the greatest thing I should have on my package, but we do. So I mean, I just think it's a really complicated issue, and the consumers who buy the food, you know, you're gonna have to deal with their perceptions.
So then you're back to using the knowledge you can gain from sensors, right? Yeah, that was your alternative.
Yeah, absolutely. And
While we're on emotional food consumption issues, a number of people have voted for this question. Is organic farming more or less sustainable?
well, I do have an opinion on that. I think it's less sustainable. So we have taken out the most difficult aspect because we don't use any chemical pesticides, herbicides, or fungicides in our process. So it's all biological control. Michael, you already talked about my sticky pads, so we know what's flying around our greenhouse, and we put in a carnivorous insect, and so we keep the population down of the thrips and the aphids and other herbivore insects that are problematic to our plants by putting in countermeasures. So what we do is we use water-soluble fertilizers like urea. Right? Urea is not a certified organic product, but you know, we're all about yield, and it's all about uptake. And so I could convert to sort of a classic organically certified fertility program. My yield would probably go down 15–20%. So therefore, my energy cost would remain the same. So therefore, I'm no longer making a salad for Main Street. I'm making it for the food elite, right? And so we started Little Leaf to basically feed people on Main Street a salad. And so if you look also, and our customers that call in and said, are you organic? And we get in, we show them the link in the USDA. We're beyond organic. Now, I mean, as far as what you can put on plants and still be considered organically certified is quite shocking. And I would urge you to go to the link on USDA to find out the various sort of nasty materials you can use and be called organic. But the people and the polls that have been done, it's like they don't want pesticide residue on the product. And from that standpoint, we check that box.
I would say one of the things that I'm noticing is that in the academic space, what is considered sustainable has become the domain of specialized research groups. So around the world, there are research groups that do nothing but really dig into the supply chain and the energy use. They really determine whether something is sustainable or not. And one of the emerging themes from that field is that is very surprising conclusions. Like, you thought this was sustainable, but if you really crunch the numbers, it's not. And I have colleagues in Singapore and all around the world who study. An example might be like an urban farm in the Netherlands to make tomatoes. You may think that it's sustainable because you're saving fuel costs, but if you crunch the numbers, it's the energy and water use in Morocco. You're better off just flying them in. And so I think that so I've been careful about using the term sustainable. We throw it around, but it's becoming the domain of specialists who can really dig into the numbers. Maybe
And so
we have someone on the panel.
And we've done some of this work, and it's very clear that organic farming is much more material intensive, sometimes more energy intensive as well. And the larger life cycle question you want to ask also is, you know, what's the consequence on the aggregate to the population? So if you're taking resources and growing food organically, that's a certain number of that's a certain amount of resources that are not being used most efficiently. And so in the aggregate, it's a less sustainable approach to feeding a large population.
Given all of the questions still piling up about various different individual ways that nanotechnology might be able to use, and I wanted to pull up one of these because it was really quite an interesting idea, Craig, that I thought
Agilent might want to see. Well, I'll see if we can find it. But the idea was, could we actually put nanosensors into plants to monitor for metabolic products that might actually be possible pharmaceuticals? And reading all of these different possible, could we use nano materials or nanoparticles for this, that, and the other thing? And then also hearing what we heard this morning about all of the different materials development. On a large scale, are we to the point of putting nanomaterials and nanoparticles to use for all of these different things? Or are we still needing to develop the technologies and the materials themselves right now? Where are we with this in the big picture?
Yeah, you just sort of expanded that question quite a bit. But to go to the original portion, would there be value in putting nanosensors into plants to look for chemicals that might have medicinal benefit? My gut tells me no, because the country and the communities are also already complaining about the cost of medications and things. So if you think about that, the cost that would be associated with each individual plant having a sensor, or 1 in every 10 plants in a field that's 200 acres or something like that, that becomes a very cost prohibitive phenomenon. I think the ability to sort of characterize the production of plants, identify plants that may have medicinal value, understand how you could maximize the yield of those chemicals in the plant, and then try to use maybe nano additions to the root structure or something like that to maximize yields. That might have value, but I don't foresee where there'd be any rational business sense in trying to monitor the plant by putting a sensor in it on its own.
So, but that question is getting at something, and that's the realization that there are molecules that may or may not have medicinal value that are only stable in the plant, or maybe metastable in the plant, and there are many examples of nutrients and beneficial molecules that we take in our food, but if we try to isolate them and grind them up and move them, they're actually very hard to analyze for it. It really makes it for a difficult problem. So there may be some value in the academic sense of probing and fishing in. That, in a sense, is part of the value of some of the technologies I'm developing in my center, is that some plant hormones and signaling molecules, it's impossible to isolate them after the fact from ground up plant tissues. You almost have to monitor them in real time, and so I just wanted to make that comment, that question's getting at something important.
We this morning, or just before lunch, heard briefly about microplastics and microfibers, and that presentation started with literally we're eating our fleece, and a number of people have requested that we talk about that a little bit more. How much of an impact might microfibers and microplastics have or be having on agriculture and our food supply?
So on agriculture, it's a good question. And I am going to enlist my executive director, Amanda Graham, if you have any ideas on agriculture. So we just launched this microplastics, and it's focused on microfibers. It started on microfibers. It eventually will become microplastics, and eventually will be plastics in the environment. The focus here is taking an MIT approach to the issue, and that is, first of all, the field is crowded right now and is becoming more crowded. In terms of understanding the dispersion of plastics in the environment, what does that mean? What does that mean to different species? What does that mean to the ecology in general, the environment, and then to human health? And so we have articulated 3 research areas, and Jeremiah Johnson is one of the faculty involved in articulating a research agenda around materials design for plastics, for polymers, that will be benign in the environment in the future. Is there a material design pathway towards reducing the environmental consequences of plastics in the environment, microplastics and microfibers. The second research area is in understanding, characterizing and isolating the amount of plastics in the environment. So understanding where it is, how it got there, being able to identify the individual polymers and the proportion of polymers that contribute to the overall microplastic pollution in the environment. And that is another team working on developing a research agenda, and then understanding how different technologies here at MIT, different fields, might contribute to getting at that, since we know very little about that. And then the third is using the latest, so big data and artificial intelligence and modeling and other methods to model, partly to understand where we are, but then also to forecast the increase in pollution, plastic pollution in the environment. And one of the reasons we're doing this is that in the late 1980s, the volume of plastics produced globally surpassed the volume of steel. That has increased exponentially. And when you look at the curves and you project out on the production of commodity plastics from the petrochemical industry, we're at the very, very small tail end of an enormous exponential curve. So what we are already perceiving as, these materials are in their environment. What does it matter that they're in the environment? What does it mean to biodiversity and natural systems generally, and to human health? We don't really know. This is another example of trying to get in front of. So what is the prospect for the future? For example, if petrochemical companies decide that, well, we need to shift a great deal of our fossil energy materials, less towards burning them for energy and more towards producing chemicals and commodity plastics. So I think that's the full spectrum of what we have launched here at MIT and the ESI. How it relates to agriculture, I'm hoping that maybe we will be interacting with JWAFs on this project a bit. But for now, we don't have an explicit footprint in agriculture. Maybe that's fair? Okay, great. I hope that answered the question.
Michael, probably a question for you here. Can you conceive of a scenario in which a nanosensor in a plant could be passed on to a seed or a fruit from that plant?
Let's see. So would it be passed on in the seed? That would be a paper in Nature if we could try to do that. Actually, that would be a very high-profile paper, a very hard thing to do. A single nanoset. So let's see if we can think about it. Well, so you can think of it in terms of a dilution. So maybe that's one advantage over the GMOs concept, which I don't want to pile on and actually disparage. But things you do genetically, if they're passed on, through the germline, then I think that there's an amplification of any mistakes or anything that's aberrant. So that scalability is not in a nanosensor. But if let me think about. Yeah, it's a tough question to get the actual context. If it's something I'd be interested in thinking more about as something mechanistically, but I think maybe as a concern. Yeah, I'm going to punt on that. I'm not really sure if it's something that we should be concerned. It's not a concern for our center. Using these materials as probes of the biochemistry itself. In the Sentinel plant itself, like if I talk to Paul about what he uses for his Sentinel plant, I think the breeding of that particular plant is a non-issue. I think normally it's a plant that attracts that's more attractive to a particular pest that would be an issue for his monocultured crops, and then so we're really just we're talking about wiring up that plant. Yeah, I guess the question of whether that propagation would occur in the wild, it's an interesting question, but it would be linear, would not scale with population. It wouldn't show exponential growth the way the proliferation of an organism would in a population. So maybe that answers the question. It's a very broad question.
We are running short on time, and I'm going to end with one last question for each of you, which I hope you will take in the spirit of friendly exploration, in no way an accusatory question. I think we have seen in the digital tech realm the social ramifications of a tech sector lacking in diversity. And that has come out in a number of social ramifications of how the technology has been deployed and how data derived from the technology has been deployed. As this field grows, what efforts are you making, or would you like to see be made to make this field as inclusive as possible and to ensure that a diversity of voices and concerns and interests are heard and reflected in the development of this technology? Craig, do you want to start us off since you're on the end?
Let's hope we can start at that. Yeah, I guess from my standpoint, it would sort of be, what do you mean by the deployment of the technology? If I look at the utilization of nanotech for monitoring purposes or things like that, I think that is all inclusive, because they're trying to protect not only the human population but also biota and things like that from things that appear in the environment. If we look at it from a food standpoint, I think this goes back to the topic we touched on earlier, and that is fully understanding the ramifications of what it is we're introducing into the food chain and how consumers will be impacted by that. Is there a health risk? Is there some other negative benefit, or is there a positive benefit that could help the human population? So inclusion, of course. I think everyone needs to have a voice, and I think the consumers need to be educated. Sometimes I feel that this need to know sometimes outpaces the availability of fact, and so we get a rush to judgment. And hopefully, if we think about diversity, that the population also gives the scientific community time that it needs in order to come up with these answers to the questions that they'll probably pose.
Thank you.
So inclusion and diversity infuses what we do at the ESI. It's baked into our DNA, just as it is at MIT, broadly. So on the one hand, that's part of the ethos and the ethics of the Institute and the ESI. On the other hand, it's part of understanding that talent is unevenly spread, and you never know where it's going to come from. And the more broadly and the more inclusive we can be in everything that we do, the research and the education and the convening that the ESI sponsors, the better the outcomes. And the other piece to this is that we are completely focused on the idea that the most robust and long-standing solution that we can provide to the world is the experience that we deliver to our students and the researchers here at MIT. And as they leave MIT or do work outside of MIT, they're going to be bringing these solutions to the world as a whole. So I think inclusion and diversity is simply part of the DNA of the way we operate.
Right, I'll second that, being also at MIT, and I appreciate MIT's attention and focus on inclusion and diversity. I'll add, and I think John articulated that perfectly there. I'll add that in moving to Singapore is also a multicultural society, and I think we have a lot to learn both ways. I think applying MIT's attention or things that MIT have learned there to the center, and also maybe Singapore also has something to teach us as well, that having a diverse population. So I think I'll just add that we're also exporting that to Singapore.
Yeah, I mean, if you're talking about the food business, you better be inclusive and diverse, right? Because all humans eat, so you don't want to basically, certainly exclude anybody. And from our standpoint, we have, European, Asian, South American, North American, men, women, gay, straight. So, I mean, to me, if you work hard, you're talented, come ask for a job. But then, most importantly, when we look at who buys our product, right, it is mostly women. I mean, and so we've done the research on that, and we wanted to attract, an educated woman, shops with her values, cares about health, is a salad lover. And we've done the data, and we've done the research. So from that standpoint, we're really wanting to focus our marketing on that particular customer because that they basically buy most of our product.
All right, well, I hope you'll join me in thanking all of our panelists for a wonderful discussion. And thank you all for all of your questions.